Thank you, Professor Reynolds. Good afternoon, ladies and gentlemen. I'm Hitoshi Ozaki from Mie University in Japan. Today, I'm going to talk about dissimilar metal joining of magnesium alloy and aluminum alloy by laser welding. First slide shows the contents of my presentation. In chapter 1, I'm going to talk about the background and objectives of this study. Nowadays, the car industry has conflicting targets of the low fuel consumption by lightening car body and safety improvement. And these targets should be achieved in together. So there is a hybrid body structure concept. On the other hand, in recent years, light materials as magnesium alloy and aluminum alloy have been used to reduce the weight of transportation equipment. But to achieve the welding technology for joining of magnesium alloy to aluminum alloy with high reliability and high productivity is required. However, it is difficult to join magnesium alloy to aluminum alloy by conventional fusion welding. So we perform this joining by laser roll welding. This figure shows a schematic drawing of laser roll welding facility. Laser roll welding was developed for joining of dissimilar metals by Professor Kutsuna. A pressure roller was mounted on a laser facility. It was developed for making of lap joints of C. At first, material A is placed on top on the upper plate, placed on top of material B. The laser hits only the upper plate. The roller conducts good contact between two seats and rapid heat transfer from the upper plate to the lower plate. The joint is made in this way. Now let's show you the video of the laser welding. In this image, arrows show welding direction and laser irradiation, roller rotation, and shielding gas flow, respectively. This welding is silent, no sputter, no arc, no porosity. Welding is over. In laser roll welding of materials with large melting point differences, laser beam is irradiated to the material with a higher melting point. But the melting points of magnesium alloys and aluminum alloys are almost the same. In this case, it is unclear which material should be irradiated with a laser. Therefore, in the present work, laser roll welding was performed by changing the welding conditions, and the influence of the welding conditions on the joint strength and the microstructure formed at the joint interface was discussed. For the materials, magnesium alloy sheet, this MPAZ31B, and aluminum alloy sheet, this 5052P were used. The thickness of the both sheets was 1 millimeter. This table shows the chemical compositions of materials used. These figures show arrangements of specimens in laser roll welding. In this experiment, two types of arrangement were examined because laser is irradiated on the only upper plate. One is the upper plate of magnesium alloy and the lower plate of aluminum alloy. The other is the upper plate of aluminum alloy and the lower plate of magnesium alloy. This table shows process parameters of the laser welding. We used the CO2 laser, and the laser power was 1.5 and 2 kilowatt. Welding speed was varied from 10 to 40 millimeters per second. Load pressure was 0.5 kilonewton. As shown in this figure, the overlapped width with 4 millimeters. Argon gas with flow rate of 20 liters per minute was used as shielding gas. As mentioned in the previous slide, we tried two types of arrangement of specimens. As surface preparations, applied graphite spray to top surface of the upper plate, and polished and cleaned the fairing surface of both seats. First, the process window was determined. The upper table shows the conditions with magnesium as the upper plate, and the lower table shows the condition with aluminum as the upper plate. In these tables, circle mark shows bonding condition, and cross marks shows no bonding condition. As a laser power of 1.5 kilowatt, bonding to a welding speed of 30 millimeters per second when the upper plate was magnesium, and bonded to a welding speed of 25 millimeters per second when the upper plate was aluminum. Also, as the laser power increases, the maximum welding speed also increases. These pictures show bead appearance and cross-section of welded joints with laser power of 2 kilowatt and a welding speed of 15 millimeters per second. The upper table shows the condition with magnesium as the upper plate, and the lower table shows the condition with aluminum as the upper plate. Regarding the top bead, a pattern appeared on the bead as the place of the laser pressing, roller pressing through it. This pattern was more clearly observed in the condition with aluminum as the upper plate. When observing the joint cross-section in the center of the table, it can be observed that the upper plate has become thinner due to heating by the laser and pressure by the roller. The microstructure at the joint interface was observed using an optical microscope. The upper pictures show the condition with magnesium as the upper plate, and the lower pictures show the condition with aluminum as the upper plate. The observed position was the center of the joint cross-section. As shown by arrows, black interfacial structure was observed on the magnesium base metal side, and white interfacial structure on the aluminum base metal side. In addition, from the size of the area shown in light blue region, it was found that the amount of interfacial structure generated was smaller under the condition with aluminum at the upper plate. EPMA analysis was performed to understand the composition of the interfacial structure. As an example, the results are shown for the condition of the upper plate of AL and laser power of 2 kilowatt and welding speed of 15 millimeters per second. EPMA mapping analysis was performed on the area surrounded by the red square in the same image. From the EPMA results, magnesium was detected on the aluminum-based metal side, and aluminum was detected on the magnesium-based metal side. In addition, the table at the bottom shows the result of quantitative analysis of the locations indicated by red dots, number 1 and number 2. From these results and ALMG equilibrium phase diagram, it was estimated that the areas that appeared white in microscopic observation were mainly AL3, MG2, and the areas that appeared black were mainly AL12, MG17. A tensile shear test was performed to evaluate the strength of the joint. The test piece shape is 50 millimeters wide rectangle. These figures show the effect of welding speed on tensile shear test per 1 millimeter of welding length. The left-hand side shows with magnesium as the upper plate by blue marks, and the right-hand side shows with aluminum as the upper plate by red marks. The laser power of 2 kilowatt is indicated by circle marks, and 1.5 kilowatt is indicated by triangle marks. When the upper plate was AL, the differences in the experimental result were small, and the average value tended to increase as the welding speed increased. On the other hand, when the upper plate was MG, the differences in the experimental results were large, and the average value showed increases and decreases. In this experiment, the maximum joint strength was 98.5 Newton per millimeter. In order to investigate the factors that affect joint strength, we focused on the intermetal compound generated at the interface of joint cross sections. As shown in the picture, the cross-sectional area of IMC shown in red region was measured and divided by the joining width, which was determined as the average IMC thickness. The graph on the right shows the relationship between the average IMC thickness and tensile shear strength. When the upper plate was AL, as shown by red marks, the correlation coefficient is high, and joint strength increases as average IMC thickness decreases. On the other hand, when the upper plate was MG, as shown by blue marks, the correlation coefficient is low. So we next focus on the joining area instead of the average IMC thickness. The left-hand side shows the fracture surface of the joint after the tensile shear test. The area surrounded by red line was measured as the joining area. The graph on the right show the relationship between the joining area and the tensile shear strength. When the upper plate was AL, as shown by red marks, the correlation coefficient is low. On the other hand, when the upper plate was MG, as shown by blue marks, the correlation coefficient is high, and therefore, it was found that the joint strength increases as joining area increases in the upper plate of MG. From the above, it was suggested that the factors that influence joint strength as the average MC thickness under the condition with AL as the upper plate and joining area under the condition with magnesium as the upper plate. Finally, I will show you the conclusion of this study. Thank you very much for your kind attention.